Welcome to breadboarding. In the previous video we looked at counters with a clock here, and we hooked it into our decoder here for our 7-segment display, and we also got it to reset when it got to 6. So effectively we're cycling through the 1 to 6 because we were also presetting the initial value to be 1 rather than the 0, and we sort of showed that if we sped this up to be a bit faster, you could perhaps use this as some form of digital dice. We had a push button there. So as we were looking at flip-flops, there's one particular type of flip-flop, the JK flip-flop, that didn't actually have the appropriate part. So now I've got those parts, then we'll look at the JK flip-flops first that we couldn't do in the previous video, and then we're going to go on to look at shift registers. So that will be the parallel in, serial out, and the serial in, parallel out. We're also going to be using a Logic Analyser to actually look at the input and output signals from that, which we're going to be using in later videos and also in the main Breadboard PC projects. So this is the slide left over from the number 11, video 11. So if you've missed out on previous videos, there will be a link at the top of the screen here for the previous video, and there should be a playlist in the description below the video where you can catch up on all the earlier ones. So we covered the set reset latch, the D-type flip-flop, which is probably the most common one used in most retro electronics, and this particular configuration where we set the input to be the inverted output. This effectively produces a toggle that it can be used for dividing things by 2. And the counter that we've just shown you was making use of flip-flops in that sort of way. Now the JK flip-flop is a particular type that has 2 inputs, J and K. The J sets the output, the K resets the output or clears the output, but it only actually takes into account during the appropriate clock signal. There's also a set and reset, or a preset and clear as they're sometimes known. The preset when low will set the output to 1, and reset when set to 0 will clear the output, and Q bar will be 1. So in the previous video I said that I had this 74LS109 JK flip-flop. Now this is a little unusual in that the K input was actually inverted, and so I thought it was going to be better to use one of these 74LS112 ones. Now if you look at a lot of designs from the 70s and the early 80s, you'll quite often find that there will be a 74LS76 JK flip-flop. Now the fact that I've had to take this from the datasheet rather than from the TI databook indicates that it actually has become obsolete. So you can't actually buy these anymore. You may be able to pick them up off eBay, but they're certainly not made anymore. And if we look at the pin layout here, you can see that the VCC 5 volts is on pin 5 and ground is on pin 13. So it's a little bit unusual from that point of view anyway. Now the interesting thing really about this is that there aren't really any pin-for-pin compatible replacements. So if we actually look at where the clock preset clear J and K are here, and then we've got the Q and the Q bar, whereas with 112 we've got clock is at least in the same place, but then we've got J, K, preset, clear, and then Q and Q bar out here. And if we even look at the 109, then that's different as well. They've got clear, J, K bar, clock, preset, Q, Q bar. So you can see here that even with these two here, Q and Q bar are actually reversed between these two chips. So none of these chips are pin-for-pin sort of compatible replacements. And if we look at the function tables, this I think comes from this data sheet, we can see that when we have the Q high and the Q bar low, so these should always be opposite, then in fact when preset is low, then Q will be set high, and the clock doesn't matter. So the preset and clear do not depend on the clock. Then when we have clear low, then we get Q is low and Q bar will be high. Now when they're both low, that's not really a sensible state to have preset and clear both low. Then theoretically they will both be high. However, it does warn us that the voltage output here may not be sufficient to meet the minimum levels. So really having both inputs low doesn't really make much sense. Now in the situation where the preset and the clear are effectively high, so they're disabled, then the main difference between this particular flip-flop and the D-type that we're looking at, the D-types generally have clocks on rising edges, whereas this clock is on the falling edge. So as it goes from 1 down to 0, then this will actually clock the flip-flop. So you can see that when JK are low and the clock occurs, then the outputs just remain the same. When the clock occurs and J is high, then we get a high on the Q and the Q bar goes low. When we get the clock and K goes high, then the Q goes low and the Q bar goes high. And then this is the thing which is really different from the behaviour of the SR latch. The SR latch, with both of these high, it would be undefined, whereas with the JK flip-flop, when both J and K are high, then we actually toggle the output. If the output was high, it will then become low. If the output was low, it will become high. And then you can see under this circumstance with no clock, then basically the outputs remain constant. So we're just going to wire up a quick circuit just to prove that that's working. Now there is one other interesting aspect of the JK flip-flop, in that we can see that if we tie both the J and K together, then the output will toggle. And if we have high and low and high, then in fact it'll actually behave like a D-type flip-flop. So in fact the JK flip-flop can be known as a universal flip-flop. If we set the J and K inputs to be the same, then we get a T-type flip-flop, which basically just toggles the output. And in fact if we connect the inverted K input to J, then in fact we end up with a D-type flip-flop. So you can perhaps see where this 109 might be useful, in that you can have one JK flip-flop, and you could also, by just tying those two inputs together, have a D-type flip-flop as well. But in general, we're normally using D-type flip-flops for most purposes. Now there was one circuit that I came across during the nanocomp project in the 6809E datasheet. So 6809E didn't have a built-in clock generator. And in fact, this particular circuit, if we wanted to include wait states or use the memory ready signal to stretch particular clock cycles, which I use to try and eliminate some of the video snow interference. And you can see down here that we've actually got the 74LS76 chips here. So when I was doing this circuit, I ran into this problem with not being able to find the any 76s. So I used the 109 and then just had to allow for the fact that these values were inverted in tying this up. So you may come across the 74LS76 in older circuit diagrams, but that can be now replaced with the 112. Just be aware that the pin counts are different. So if you just turn this off for the moment. So this is the 112 chip. Local supplier Bitsbox doesn't do the 112. They do the 109, but not the 112. So got 3 of these. I've already put a chip label on one of them, so we're going to take this out and I'm just going to wire up the board to test this. We'll come back when I've wired that up. Okay, so I've wired up our JK flip-flop here. I've only wired up the one side. So what we've got is the Q is the green output, red is the Q bar, then the white lead is the J input, the orange lead is the K input, and then the clear is black and preset is green there. So, and then we're using the clock over here. So if we just turn this on. So this is our 555 timer over here, and it's set at a very, very low clock frequency. Now, in fact, the clock, which is over here, it's when it goes off that we should actually get the state change will change in the flip-flop. So at the moment you can see it's defaulted to 1 when it comes on. So if we just try the clear first of all. So if we do this whilst the clock light is on, we should see it still happens as soon as we actually go to 0 volts. So clock is on. The clock doesn't make any difference. If we now do the preset and preset. Now if we put both preset and clear on, we'd expect both lights to come on, and in fact both lights do come on. that's not really a very useful state to have things in. So we've got the output set to 1 at the moment. So I think what we'll just try and do is to put both J and K to be 5 volts to start with and see what happens. We'd expect it to toggle when the light goes off, we'd expect it to toggle. Okay, so I've got to the bottom of what the problem was. So we were originally taking the clock output from our NE555 timer here, straight in over here. Now, once I looked into it a little bit, there is actually something in the datasheet that says that the rise time and fall time for the clocks and the set and preset signals need to be within a certain amount of time. So if you just have a quick look at that. This is our 74 LS1010A datasheet, and the bit that we need to worry about, here we go. So it says that there is a time for low to high and high to low for clear, preset and clock. What it says is the maximum time there should be 20 nanoseconds. Now, in fact, when I put an oscilloscope on this, what I found is that it was a very brief sort of 20 nanosecond period where the output did actually toggle. Let me just show you what I did to fix this. So I think the problem is that the output from the timer there, probably with the LED on it as well, didn't help, was actually not rising and falling fast enough. So what I've done is I've just put it into 2 of the spare gates we've actually got over here. So we'll just move this down a little bit. So we had this sort of NAND gate over here. So all I've done is I've made an inverter into another inverter. So the output is basically just buffered. And so what's happening now is we're taking the clock output from here into here and then into here. So hopefully this chip will have cleaned up the signal a little bit. This one didn't have quite the same sort of timing requirement. And so, although it's going a little bit too fast for the camera to pick up the flashing reliably there, but we need to have it flashing at a fast enough speed so the oscilloscope can pick it up. So if we have a look at the oscilloscope output, so I've got the oscilloscope probe. One is on the clock output here, so I think that will be the yellow signal, I think. And the other one is actually on the clock input, which is the output from the buffer there. So this is the oscilloscope. Everything looks okay. There's a little bit of bounce there, but if we now zoom in and down to about the 10 or 20 nanosecond level, so this is now at 10 nanoseconds per division. And the blue line here is the clock input to the actual flip-flop chip, and that's coming from the buffers. You can see that it changes about here, and it's got down to the low level within probably about 10 or 15 nanoseconds. But this one here, the yellow line, is actually the output from the NE555 timer, and you can see that this is actually taking quite a bit longer. So it's taking at least 1, 2, 3, 4, possibly 5 divisions here, so that's at least 50 nanoseconds. And so because this clock, because of the way how the circuit is wired, so apparently because this has got a master-slave flip-flop, then in fact it relies on the fact that the clock signal here and the clock signal here on the 2 internal latches in here, and these rise and fall time requirements are actually necessary. So in fact, when I did look at the output here, there was a very brief sort of pulse, but because this clock input wasn't fast enough, then it wasn't working properly. So even with the simplest circuits, sometimes the rise and fall times can catch you out. And if we look at the rising edge, so this was a falling edge, which things are triggered on. If we just have a quick look at the rising edge as well, and you can see there's a similar longer rise time here. So from here to here is probably at about 10 or 15 nanoseconds, but from here to here is probably more like 80, 90, 100 nanoseconds. So because our NE555 timer clock is probably not quite fast enough for our flip-flop to be happy with the output signal, that's just something we need to bear in mind a little bit later. So if I turn the clock back down again So we can now see what we were trying to do, prove here, is that when both J and K are set to 5 volts or to 1, then we get the two toggling like that. If they're both set to 0, then they should just preserve the previous value. We slow this right the way down. They're just going to clear this first. It's cleared. So when we set the J to 1, then we'd expect the green light to come on, but it will only come on when the clock goes off. So we'll change this when the clock comes on, and then it should switch back when the clock light over here goes off. If you see it, it actually changed that clock time, and if we do the same with the clear, then the K clearing the output only happens when the clock is occurring. So it just goes to show that even the most simple circuit like a flip-flop here, that if we don't get the input correct, I think this one is particularly sensitive because it's the falling edge rather than the rising edge. We didn't seem to have the problem with the rising edge, but the falling edge on the JK flip-flop caused us the problem. So that was an interesting diversion. So even the simplest of circuits like you were looking at with this flip-flop here, because I hadn't read the datasheet to check that the clock rise and fall times were within the tolerance of 20 nanoseconds, then in fact that caused our problem. So when we were trying to see if things were toggling, then in fact they didn't toggle because the clock fall time was not within the tolerance on the datasheet. So the next thing we're going to look at is shift registers. Now, shift registers can work in sort of two modes, and these are two of the sort of shift registers which are used in the IBM PC, PCXT in particular, around the video card in particular. And probably the easiest one to think of is the 8-bit parallel load shift register. Then what we can do is we can put 8 bits of data in here, and then based on the clock, then the output will then cycle through each one of these as the clock changes. So in particular, we'll have a look at the circuits where these are used in a few minutes. So this one is used to take the parallel data here and then to send it out 1 bit at a time based on the clock here. And this is used, for example, for taking the raster image of a character in the character ROM on the video cards and to actually serialize the output here to drive the video output signals to decide whether we want to show foreground or background. This one over here is not quite so commonly used, in that what this allows us to do is to take a serial input here. So we've got an A and B input, but basically we just need to worry about one of the inputs. As long as the other input is held high, then it will just be the other input that determines things. And this will allow, again, with the clock signal, to be able to take in a serial input and then to make it available on the outputs here. And this would, for example, be used if you were looking at taking a serial input, say from a serial port, for example. You could then turn it into byte values. Now, as it turns out, the dedicated serial port chips that we tend to use do a lot more than this and have all sorts of things to do with the start and stop bits and synchronizing clock and all that sort of stuff. But if we were having a synchronous clock, i.e. we're having a link between two circuits where we have a common clock, then this would allow us to send the data over a single bit rather than having to have a parallel interface. So if we were trying to send data perhaps over hundreds of meters, for example, which is what we use serial ports for in the past, so the RS-232 serial port could probably drive things over up to about 100 meters at least. So if we were trying to do serial ports, then this is the sort of thing we would use. So if you just have a look at where these were used in the IBM PC, first of all. So the 74LS166, which is the parallel to serial, is used in the CGA card. So this is the color graphics card here. And if we just zoom in, there's two areas. The first one we talked about was the character generator ROM. So based on the character values coming in here and the line of the row of the character, which is coming from the cathode ray tube controller chip, the raster image of each row of the character comes out here. And then based on the dot clock, which is the clock for each individual pixel, and the shift load signals here, then that value will get loaded into here, and then the output then goes off to the change dots here, which determines for some of the other logic whether or not we're showing a foreground or background dot for a particular character. And then over here, they're also again used for where we're actually doing graphics mode. We're sending out the character and attribute values, and basically this is serializing the graphics character values to produce the C0 and C1 colors. So this can do up to 4 colors in the CGA graphics card, and then those are then coming in to determine what sort of colors we're actually showing coming out for the video card. So basically those chips, so the parallel to serial is used quite a bit in video output circuitry, and then the serial to parallel, there isn't really an example for sort of serial communications, but there is another part of the color graphics adapter which is actually to do with generating the TV color composite signal. So this is necessary to drive, say, the NTSC color signal for a composite output on the CGA card. And in fact, the 164 is in fact used here. So it's really used to extend and change the timing of the horizontal sync and vertical sync. So it's used to effectively delay some of these input signals by a number of clock cycles, and to, with the gates and things, is used to actually extend the period of some of those things for the TV specific timing. So it's a bit of an esoteric one. That this one's a little more difficult to come up with sort of the easy to demonstrate examples. What I'll try and do is to use the parallel to serial one first, and then perhaps we'll feed the output of that into this one and see if we can reconstruct the data that we're sending. So if you look at the data sheet, so this is the parallel load shift register. So we've got our A, B, C, D, E, F, G, H. So those are the parallel input. This is the output, QH. Now we have a couple other things. The clock inhibit we can just tie to low to 0 volts and it will be disabled. Clock is our input here. Now the serial, we're just going to tie that to 0 volts, in that that's what the CGA card did. What this needs to do is to load the values in here. The parallel, we need to have the shift load go low, and then once this is high again, then in fact this value here will get shoved in at the far end for each time we shift it. So effectively 0 will come in as we actually shift the values out. So what we're going to do is to wire that up and put in a fairly low oscillator. Perhaps might tidy it up like we did with our flip-flop. Then we'll see if we can see the output sort of toggling as we put in different values for the A to H here. Okay, so I've wired up a 74 LS166. So this is the parallel in, serial out. So we've got our parallel in over here. So this is just the dip switch, and I've got alternating ones and zeros. So it's a 0, 1, 0, 1, 0, 1. So the top bit is actually set, and those are going into the A through to H inputs. The output is actually connected, so QH is actually connected to that LED there. This is just another LED from the clock over there. And I've got various signals here. So I've got the serial in. Now serial in on the CGA card is defaulted to 0 volts. So it just means that if we don't do another load of the values in after 8 clock cycles, then all the subsequent values will all be set to 0. Now generally what happens with the clocks on something like a serial card is you'll have the load will occur every 8 cycles. So basically once the data has been shifted out of that shift register, then it will load in the next lot for the 8th clock cycle. So we can perhaps have a look at wiring up that a little bit later. But for the moment, I'm just going to switch this on. So what we'd expect to see then is, because when we load the values, we expect to see the output probably about half the frequency of the input there. And after we've had about 4 ons, then we'd expect everything to go to 0 because the value of this one here is then going to take over once we've done our 8 clock cycles. So to start with, we can see that our clock is going on. It's the rising edge of the clock that things should happen. So to start with, just going to clear everything. So this is clearing everything. And now we're going to do a load. So we're just going to put it to ground for a cycle. So it's on, off, on, off, on, off, on, and then it should be off from now on. So because we've done 8 cycles, then it's the value of this one here. Now, if we now set this to 5 volts, after about 8 clocks, we should see this light come on. So that's about 3, 4, 5, 6, 7, 8. There we go. So after 8 clocks, because we've loaded the serial in, has gone in at the least significant bit, and after about 8 clock cycles, then that one will work its way through. And similarly, if I now connect it to 0 volts, by the time we've got 8 clocks, then it should go off again. 1, 2, 3, 4, 5, 6, 7, 8, and it's off again. So it's a bit difficult really to see the data because coming in serial out, it's probably easier to actually hook up a logic analyzer. So what I might just do now is I'll get a simple logic analyzer. I'm going to hook that up, and then hopefully you should be able to see the outputs here a little bit more clearly. Okay, so I've wired up my simplest of logic analyzers. The LA1010 is the cheapest. The only issue is it doesn't have any onboard memory, and so sometimes when you're trying to hook this up to high frequency signals like, say, a video card, then it can't really handle the speed needed to be able to do more than a handful of signals. So the LA2016 is the other one I've got, which is more capable, sort of in the intermediate price point. There is a 32 channel one, the LA5032, but that's £300 or £400, so it's quite a lot more expensive. It is very nice to be able to have 32 channels on the screen at the same time, but I would start perhaps with the 2016 is probably the sweet spot for the performance and the price. So if we just have a look at the software that we've got for this. So this is the KingSFIS software. It allows you to decide how many of the channels you're using. So you've got 16 channels here, there's a few turned off. We've got our A to H here, and we've also got an analyzer here. So this allows us to say, can you work out what the hexadecimal value is for the first 8 lines? That's not going to change very much because it's static from our switches. We're saying we want to look at the clock, and we're going to trigger the collection of the data here on that. We've also got the shift load, clear, the output, and the serial in. So the serial in is going to be 0 by default, but we might change that whilst we're actually doing this experiment. So we're taking 20,000 samples a second, which is about the slowest it can do. It can go up to sort of higher frequencies, although with this particular model, if you choose the higher frequencies, you might only be able to record 1 or 2 signals at the very highest level. So generally, it'll go up to about 1 or 2 megahertz with most of the channels without too much trouble. If you're doing video frequencies at sort of 25 megahertz, then it is a bit more limited. So I'm just going to run this, so it'll be waiting for the clock signal to start. So I've got this wired to clear first, so when it starts, it should be in its cleared state. So we'll undo clear, and now I'm just going to press load. So we've still got our alternating 1s and 0s on there, and we'll see that the green light there will flash at a different frequency from the clock because it's alternating 1s and 0s. And then after it runs out of data, it will then just go to 0. It's now on 0s. And if we now change the serial in to be 1, after about 8 clocks, we should actually get the light coming back on. That's now back on. And if we set the serial in back to 0 again in about 8 clocks time, it should go off. and it's off again. So we can stop that now. So if we have a look at the values here, you'll see over on the right hand side here, it started with 0 there because obviously at the very beginning there weren't any values because the power was off. Then as soon as the power was connected, then we actually have got AA there, which is basically alternating 1s and 0s. We don't really need to worry too much about the first half here because this is static, but obviously if we were taking data from a counter, then this would be changing perhaps with the counter. And we can see here that we've got our clock values. There is the first time we do the shift load, and then we can see that our output then is toggling as the data alternates and is shifted round. Then you can see it goes to 0 when we run out of data for about 8 clock cycles. Then we've actually changed the serial in to be 1. So again, after about 8 clock cycles, we'll then have the output enabled again. And one of the nice things that you can do with this is you can add timing markers. So for example, once we've run out of data here, so the last value for the least significant bit was 0 in fact, then we can sort of see how many cycles we've got here. And in fact, we can even count pulses as well. So if we wanted to, we can say choose channel 8, and we'll choose A, and it'll tell us how many clock signals and things have actually occurred between certain periods and things. So in fact, when we set this to be 1, it takes this number of clock cycles before. So you can see here that when we set this to 1, then it will take 8 clock cycles for the output here to actually go high. And we can see here it's counted the number of pulses between A1 and A2 for channel 8, which happens to be our clock. So using a logic analyzer like this makes it a lot easier to try and track down problems. And you can see here we've just got our alternating 1s and 0s output there. If I change this to be a different pattern, so perhaps if we do 1100 1100, and we'll try that again, we'll just save this so we can look at the data later if you want to. Now the only frustrating thing about this is that you can set glitch filter settings. So for example, when I was plugging the cables in and out, there's no debouncing, and so I was getting some glitches on there, and you can actually set a glitch filter at a number of samples. Fortunately, there's a bug in the software that sometimes it will crash and it will lose all the data that you've got, so you really need to make sure you save your settings once you've set it up. And needless to say, I hadn't done that, so I had to set it up again. So it's good software apart from the glitch filter settings. You really want to set the glitch filters before you've got any data. Once you've got data, it does tend to crash. So we're going to run this again now, and what we're going to do this time is we're going to set the input data to be a slightly different pattern, and then we should actually be able to see that the pattern here will be a lower frequency. I'm just going to turn the power off and just going to go back to our... So it's in clear to start with. Switch on. And I'm just going to set the switches to 1100, 1100. So now we're going to do load. Oops, need to turn the clear off first. So clear is off. Load. And now it should be sampling. You can see the light is flashing at a lower frequency than we had last time, because now we're doing 2 1s and 2 offs. And then when it's run out of data, I'll just stop the capture and we'll go back and have a look at it. So you can see this was where I was configuring the switches. So we started with AA, and now we've got CC, which is 1100, 1100. And what we can see here then is we have got a few glitches and things here. There are glitches on the clock. I don't really want to change the glitches on the clock just because it may very well crash. But we can see here that we've got our shift load here, and that this time we've got only 2 wider periods here, because now these periods are actually two periods each. They've got 2 on, 2 off, 2 on, and then another 2 off. So we can see that the shift register is rotating the bits, so it takes the highest bit first, so H is the first one to go out, and then A is the last one to go out, and then once it's run out of data, serial in is the one that replaces the subsequent values out after that. In general, what we would do is to make sure that every 8 values that we actually load a new set of data in. That was the 16674LS166, the 8-bit parallel load shift register. So this was loading parallel values in, and then the output was coming out of here. And this one is a parallel out serial in. So what we're going to do is to connect the output from here to the input here, and then I'm going to put the logic analyzer on these outputs. We're going to connect the clear and the clock signals together. So effectively this is a synchronous communications interface effectively, and then we'll see whether or not we can get the values that we're putting in here to come out here. So I'm just going to go and wire that up, then we'll rewire our logic analyzer so we can actually get the output from here. So just have a quick look at the data sheet first of all. So this is the 74LS164. This is the parallel out serial shift register. So basically we have 2 inputs A and B there, so as long as we tie one of those to 5 volts, then the other one will be the input. We have a clock and a clear, then we have the output QA to QH. So it's pretty straightforward. So all I'm going to do is to wire the 2 clocks together and the clears together, so we don't really have to worry about them getting out of step. And then what I'm going to do is put the logic analyzer on the outputs here, and we're just going to feed in the alternating 1s and 0s, so the AA that we had in the previous one. So I've updated the configuration here, so now we've got QA to QH, so we expect this now to change. We'll see the clock, shift load, clear. Now I'm triggering it on clear now, so when clear goes from low to high, then it will start capturing stuff. So hopefully we should actually be able to see the data AA coming from the input to the 166 shift register, and then it should be shifted out to the 164, and we should at some point see AA appear on the list here, and that means at that point in time we've actually successfully transferred the data. What will then probably happen is it will then change back to 0, and once it's down to 0, what I'm going to do is to set the serial in to 1, and then we'll wait until the outputs all go to 1, so we'll have FF. And what that will basically mean then is that we've sent the original data, then we sent all 0s, then we sent all 1s, and then we'll finish the test. So I've put in the extra chip here, so this is the 164, and I've just wired in the clear and the clock together, and then the output from our shift register here, the orange line, is now going into the input to this, so it's going into B, and A is just tied to 5 volts. So just going to power this on, so the clear is currently enabled. So now we're going to undo clear. We'll do a load. We just need to wait until the green LED stops flashing, then count about at least 10 cycles after that, and then we're going to change the serial in to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now we're going to change the serial in be 1, and then hopefully after about 10 or 12 cycles, then we should be seeing FF appearing on the logic analyzer coming out of our serial in parallel out. Let's go and stop the logic analyzer. Right, So let's have a look. Needed to be a little bit more patient and leave it a little bit longer because in fact it only got to 7F, it hadn't actually got to FF there. But what we can see here then is when we did our shift load, then we've sent the output, and the clock really only starts once shift load has gone high. So you can send that we've sent a 1 and a 0, 1, 0, 1, 0, 1, 0. So that should be AA. And we can see here that as the data's arriving, it's getting shuffled along up to here. And that in fact, at this point here, we see we have AA. At this time point here, we do actually have AA, and we can see up here. So if we put a timing marker in here, so at that point, we have actually then got AA. But because the serial into the 166 chip is set to 0, then basically we're just getting zeros coming in until eventually the value gets down to 0 here. We've got 0 here. And then when I change the serial in to be 1, then we can start to see we've got a 1, a 3, 7, and I was just a little bit impatient. If we'd have waited for another few seconds, then so we've got 0, 1, 3, 7, F, 1F, 3F, 7F, and we would have had FF if I'd have just waited another second or two. So what we can see then is that we've taken the AA value going into the parallel in serial out, and then we've sent the data over a serial connection. Now we did require a common clock and a common clear, and really when you're dealing with RS-232 and things like that, then you don't have a common clock. You just need to make sure that both of the receiving and sending ends are running at the same frequency, and the start and stop bits is how the communication manages to work out whether or not we need to clear the data and start a new bit of data. But just shows that we've managed to get the serial output and serial input registers working. So I was originally going to cover the buffers, latches and bus termination, but it's probably already got long enough with some of the complications around the clock for the JK flip-flops and obviously the shift registers. It's probably taken a little bit longer. So I'm going to break the video now, and in the next one we'll do the buffers, latches and bus termination. So this is how can we run high frequency signals over long wires and bus rails, and what sort of termination can we use to minimise some of the interference we might otherwise get. So in this video we've managed to test out our 74 LS166 parallel in serial out and our 164 serial in parallel out. So we've managed to prove that we've got the same data going in and coming out. We've also played around with the JK flip-flop, but I've also introduced you to a basic logic analyzer, one of the ones I use, and hopefully this will set us up for the next video, and we'll be able to perhaps use the output from these counters up here to feed into our bus rails and be able to look at things on our logic analyzer. So if you don't want to miss out on future videos, then please hit subscribe, and if you found the content useful, please hit like. It just helps to make it available to more people. Thanks for watching.